Where do chemoautotrophs get their energy from?
Extreme climates.
From the broken bonds of what?
Like
Chemicals that are found in
Extreme climates.
extreme environments. That's right. Because in very extreme environments, extreme chemistry happens, and those bonds can't last forever. So when bonds of extreme chemistry are brought to the world where we live, then they often break, and that energy is useful. All right, well, done with all this. I mean, maybe not. Anyone have any question? Are we done with all this? Oh, one more. I forgot to do this one. Students, what does it mean to affix something? Like, I want to affix a mirror to the wall. Yeah. To attach, to stick on, to bond something. Does that make sense? Everybody knows that? To affix. Have you heard that word? A-F-F-I-X?
Yeah.
So please look up carbon fixation or carbon fixers. Carbon fixation is when you attach carbon into a bigger compound. Carbon fixers are organisms who attach carbon. Fixation is to fix, is to attach. So carbon fixation is to attach carbons.
To another compound?
Yeah, or into a big compound, yeah. Carbon fixers are organisms that do this. A plant is a carbon fixer. Okay, so now it's number 50. This is the living stuff, usually about in balance, roughly, kind of, like up and down, steady equilibrium. I need to warn you that this one over here has a lot less words to fill in, but probably a lot more words in your notes. Right up here, underneath the 15, it's probably tough to see it. I have the human and flower cycle like you saw over here. That little thing is the biotic cycle, and look. But sometimes things leave that cycle. Like you drop skin cells, or plants die, or you die, or you and or plants have little waste products. Please look up. For the sake of conversation in the carbon cycle, I'm going to call that leakage, which is not a science word. This is a Jose term. What I mean to say is, some amount of carbon is lost from biotic systems. You know, because stuff dies and gets hit by cars, and poo happens. Skin cells fall off, leaves fall off. It's okay? Now, as an example of leakage, let's imagine that I were to kill Martin or Kai and throw their corpses over that fence into the bushes and leave them to decompose there. Does everybody agree with me that pretty soon all of the atoms in them would go into other living stuff? Their atoms would become songbirds and butterflies and wildflowers, right? Because the crows would pick them apart, the rats would nibble them up, the ants would break up stuff, they would burst and the juices would flow out, the worms and the maggots, beetles, even their bones would eventually be chewed on and then ground up and then go back into being calcium dissolved in water for life somewhere else. Please look up. Most leakage is recycled by decomposers, but very, very rarely, some material exits the biotic cycle? Very rarely. Don't focus too much on your drawing. I notice a lot of you trying to get the arrow right or whatever. I'll leave that up there all day tomorrow too. But here comes a key issue that I need everybody to focus on really fast before you can, don't miss this issue. How is it possible that I might throw Kai or Martin over the fence and they would escape decomposition? How might they leave the biosphere? Yeah?
If it was really cold.
If it was really cold. Okay. Like, so much that they would freeze solid and nothing could break them down?
Yeah.
Had to be really cold, but yeah, that's possible. If it was like -30, nothing would digest them. What else?
You threw them in a river and they became fossilized.
Well, if I threw them in a river, oh, you said fossilized maybe, but rivers don't make fossilized. If I threw them in a river, they'd be eaten by other decomposers. So what are we missing? Yeah?
They were carried by water into the rock layers and stuff.
Yes, but are there like rock layers, like open mouths waiting to eat water and then make a sandwich? Is that how rock works? What is the process, it's not written on the board, that would keep the lump of Martin or the lump of Kai from becoming more living stuff? How could I turn them into rock? Yeah?
They were covered by sediment.
Bingo Yahtzee. Right on the nose. Nailed it. If they wash down into some bay, let's imagine the Santa Barbara Harbor was a natural bay, which it's not, but can we just do that? A shallow body of water, relatively still, okay? If you throw your lumps of Martin and Kai down into the harbor, right now, there are seething masses of organisms that are picking through the bottom of the harbor to eat whatever we put in there. Worms and little bugs, and I don't know what the hell's down there, but they're all just eating. Recycling. As a matter of fact, the bottom of the ocean is a great place to dispose of a body. You may have heard of this. Inspiration. Always stay by the coast. But every now and then, through some sort of fluke or act of Jah or whatever, layers of sediment might bury those decomposers so far that they run out of life and nothing can reach those ingredients. Imagine like a giant mudslide. If there's like a big wildfire and then the erosion all hits at once, so when you get a big storm, there's like 3 feet of sand on top of everything, that might be enough to kill all of it. And you'll end up with sand layers, a sediment-rich layer, you know, an organic-rich layer, and then more sand on top. Everybody got this? This is the secret recipe that barely ever happens. An insignificant percent of leakage escapes decomposers and ends up in rock. Yeah?
Does it have anything to do with pressure or just a sediment layer on top?
So far what I've said, we haven't done anything except take some organic compounds and put them away from the biosphere. Pressure comes later. Will you put these together for me? Put these together for me. All right. If there's a place where I can bury carbon to take it away from the biosphere, does anybody know what we call those places where carbon is stored away from the biosphere?
Oh, sink.
That's right. This is called a carbon sink, which is any place that carbon is stored away. Yes?
Which layer is the carbon sink? Is that the one that has the carbon-rich layer?
This.
Okay. It's just like the one where it goes
It's a place.
when it exits sink.
a carbon sink is a feature, a thing that puts carbon away for the long term.
Should we
Does
Like a
that,
bank.
lithification? Is-
You can write whatever you want.
does that have to be substantial amounts of carbon or just carbon in general?
We're not saying how much. So, let me see if I can say this better than I've already said it. Maybe you already heard this. But let's make sure that this is feeling right. Most carbon that you and I know is transferring from one living thing to another. You breathe it out and something else breathes it in and they make it into sugars that are eaten by you. And then you breathe it out and then it goes back to make a plant. It's eaten by a cow and the cow breathes it out. Some amount of carbon in, some amount of carbon out. Cool? Biotic? Yes? And most of the time, even if you die, it's not the end of the biotic cycle because there's another layer, which is the decomposition, the recycling between organisms. The detritivores that eat all the waste of life. Yes? Yeah.
So wait, what's the difference between a detritivore and a decomposer?
Not much. But sometimes, little bits, like a leaf or a turd or an insect or a dead organism altogether, sometimes they're carried by water to enter the rock cycle in a carbon sink somewhere. And if you get a sandwich, please look up, of much sediment, a layer with a lot of carbon, we'd call that an organic rich or a carbon rich layer. On top of more sediment, sometimes you make the perfect sandwich. Because watch this. Let's review. What did it take for me to stick two carbons together? Energy, right? Do we agree? That with energy I have force carbon bonding? Yeah? So, pay very close attention. Let's imagine that I have buried one lump plus another lump plus another lump under a lot of rock. Do y'all realize that if you have a really, really big pile of rocks above you, that adds a lot of pressure to you? Yes? Because there's a lot of mass being acted on by a whole lot of gravity. Do you agree? Yeah. And does everybody know that heat and pressure are just energy? Yeah, so watch this. So much energy. Now, what you see right there, that could be jet fuel. This is what they're running jets with. This is about airplane fuel, because that's roughly 18 carbons all stuck together. Does everybody realize that our modern economy with petroleum and natural gas and coal, we're not interested in the carbon, right? Do we do anything? Like, do you put gasoline in your car because you need more carbon for it? And just like the sugar and just like you, the carbon is just like a, get the crap out of the way. What do I want out of this?
Energy.
Right? The little carbon bonds? Yes? Do we agree with all this? Everybody following me? In special places. You can just stay like that all day. You're doing great. Nobody needs notes. Just do what you're doing. In special places where sediment will sandwich a bunch of carbon, over time, heat and pressure, sediment plus carbon plus sediment, will lithify, make a rock. And anybody know what we call those rocks that are a bunch of carbon stuck together in the process of making rock? Coal is one type of fossil fuels.
The problem is that
And you know, all my hippie environmentalist friends, we always poo-poo fossil fuels because, of course, fossil fuels are the source of many of our modern global problems. But let's put that in perspective. This is a lot of bonds. And there's not a lot of other stuff there. You probably know that lettuce, for example, that's a whole lot of work for a little bit of energy. Can you imagine how much lettuce you'd have to chew if you were going to run your entire metabolism on the carbon bonds of lettuce? It's a lot. If you don't know, it's like a milk crate per day. That's not fun. But fossil fuel is just the carbon parts. Because when you do this, you squeeze out most of the water, and you squeeze out a bunch of the other stuff that doesn't actually become bonded. So the nice thing about fossil fuels is it's pretty much just straight up energy. Anybody have any way to estimate how much calories are in a gallon of milk? A gallon of milk.
Or maybe 800.
800? Yeah, anybody else serving, in a pint, how much you get? My guess would be maybe 6,000 calories or something in a gallon of milk. If you drink a gallon of milk, that's
2,400 calories.
2,400, perfect, beautiful, okay. Anybody know how many calories are in a gallon of gasoline?
20,000. 250,000.
31 million. 31,000 thousands. Here's another. If you were going to replace the work done by 1 gallon of gasoline, you would need something like 16 days of human labor.
How much gasoline?
For 1 gallon of gasoline. You would need 16 days worth of human output to push your car at that speed, that distance, that you use to consume 1 gallon. So fossil fuels are holy crap, so much carbon, awesome. And we figured something out. Please look up. It's not about the carbon, but if you can go like this, and you go yee-haw, and you put it in a barrel, and you become president, then you put that stuff into the pump, and you put that stuff into the car, and then your car has some fancy engineering to make the right fire at the right rhythm with the right oxygen and the right amount of gasoline. You can go vroom, and you can run over old ladies and children. Because inside your car, there's these little spaces built to go chop, 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 and get all the energy out of all those carbon bonds. So much energy. So much energy. Chop, 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 chop. So much energy. And so your car is happy. Chop. And you're happy, and I'm happy because we got all this free energy from the job. We can use that energy to replace human labor and make goods cheaper. We can use that energy to build fancier houses and bigger bridges. And we can build dams that provide water so that we can move in the middle of nowhere. The things that we can do with this energy that have led to modern society. Put a man on the moon. Yes! And the reason that I mention is, there is a problem, right? There's a whole lot of carbon left over. I can explain this in the last 2 minutes, but this would be a good time to be awake, if you were awake. For one thing, a very small amount of carbon becomes rocks, and please look up, that carbon would eventually come back out of the rock. Do we agree? Because there's a rock cycle. So rocks are made in lithification, and they weather in weathering, right? Rocks are dissolved by water. Rocks are evaporated by volcanic eruptions. Everybody knows that, right? And that's pretty slow. If you imagine how quickly your mountains are wearing away, as a global average, that's about how quickly rocks are being built. Slow, right? Humans, on the other hand, in this part of the equation, we found a shortcut. You see, from living stuff into rock, through volcanoes and weathering back to living stuff, that's a teeny bit of carbon over a long period of time, about 500 billion years on average. Carbon is in rock for about 500 billion years. Sometimes, I don't know, maybe I'm wrong, 500 billion years? Whatever, it's a long time. But humans, we found a shortcut. We figured out how to break the carbon bonds out of the rock. We still haven't figured out how to put it back into the rock. So what does that mean? We have way more CO2 around. Way more. We found a shortcut to get it from the rock. No shortcut yet to put it back in rock.
Never had that.
Dang, Amin will remember to stamp both tomorrow.
Oh.
Thank you, children. Bye-bye.
So